We probably will get pretty close to finishing up this chapter today. If not, we'll be almost there. And remember, this is the end of the content of the material. This chapter is the end of the content of the material for our upcoming exam, which is next week on Thursday and Friday. And again, you can take your exam on either day, so it works out fine. Going back to glomerular filtration, again, it's a passive non-selective process, so that means all kinds of things get through, and that's why the next part says allows passage of all except for actually significantly sized proteins and our blood cells, red blood cells, white blood cells, and platelets. Those types of things shouldn't get through. Net filtration pressure is G for glomerular hydrostatic pressure. Remember, that's going to be related to blood pressure. Hydrostatic pressure inside our vessels is always related to blood pressure. Minus the combination of glomerular osmotic pressure, because since hydrostatic pressure is pushing pressure, remember osmotic pressure is pulling pressure, so there's always that counterbalance in capillary dynamics. C in this case stands for capsular hydrostatic pressure, and that's basically back pressure. So as that capsule fills up, the more you fill it, it won't take any more if it's completely full. So you can't actually make any more filtrate if it is not draining off properly. And that draining point is going to be the tubular system, the proximal convoluted tubule, the nephron loop, and the distal convoluted tubule, as well as the collecting duct and various other areas. And so this is important because if we have a stone out here in any area, what does that mean to the drainage of this system here? It's blocked. And so what does that mean to the number for capsular hydrostatic pressure? It goes up. And so that's an important aspect. Stones are bad for your kidneys because they actually block the outflow of the filtrate. And so when that happens, then you actually ultimately, if it does not relieve itself, you ultimately will destroy some nephrons, and that's not a good thing. So we only need, in order to make our normal daily volume of urine, which is 180, or daily volume of filtrates, let's be a little more specific, which is 180 liters a day, you only need 10 millimeters of mercury pressure to actually do that, to have a nice continuous flow of formation of filtrate and then flowing down the tubular system. So we have, again, our pushing pressure, we have our pulling pressure, which is osmotic pressure, and pushing back is at capsular hydrostatic pressure. I decided to show you the numbers, but we want to use just easy rounded numbers. So we're going to use 30 instead of 32 for our glomerular osmotic pressure, and we're going to use 20 instead of 18 for our capsular back pressure or hydrostatic pressure. And so we went ahead and changed our numbers in various areas, even down here in this range. The other thing that can affect filtration is the diameter of our blood vessels. The one that is the easiest to control is the afferent arteriole. And so if I vasoconstrict the afferent arteriole, what will that do to our glomerular hydrostatic pressure? It decreases that. So that will also decrease the amount of filtrate produced. And indeed, in fight, flight, or sympathetic dominance, we have constriction of that afferent arteriole causing decreased filtrate being formed, and then decreased urine formation. So that does make sense. We want to save our fluids for this, tremendous effort that we're going to put forth to actually save ourselves. And so that system works very well this way. Yeah, it's always coming. You can change the diameter of the efferent arteriole, but remember the one that's actually part of the macula or juxtaglomerular complex is where we actually have that afferent arteriole and the DCT coming into contact with the glomerulus itself to actually monitor solutes and actual pressure or hydrostatic pressure inside those specific vessels are part of the monitoring of the filtrate. If we actually did dilate for example, if we did dilate the efferent arteriole, what would that do to our glomerular hydrostatic pressure? Make it go up or make it go down? Make it go down, because remember, the narrow efferent arteriole causes the larger afferent arteriole to actually have more hydrostatic pressure or more back pressure in that area. So we can actually modulate both arterioles, but the one that's the easiest and that was designed for the easiest manipulation is the afferent arteriole. So glomerular filtration rate is abbreviated GFR. That's 180 liters a day, and that's due to what we just discussed, the net filtration pressure. And that actually averages out to 125 cc's per minute. And so sometimes when people are in the hospital, they actually will collect their urine, and they are actually, in that process, they're actually monitoring the health or integrity of their kidneys by measuring their actual GFR, as well as certain products that they are excreting in their urine. 3, regulation of filtration, we've actually just already discussed, but let's go through the notes a little bit again. Autoregulation, again, we like the afferent arteriole to adjust its luminal diameter, which is also related to vessel diameter, to maintain a relatively constant blood pressure and therefore glomerular hydrostatic pressure and flow. So autoregulation is actually a myogenic response. We mentioned previously, if for some reason the vessel is, the lumen is dilating, then the smooth muscle in the vessel wall detects that and actually has a constrictive response to that. So if lumen dilates, vessel constricts, and vice versa. And again, this is a mechanoreceptor response. So this is this is the main way that we actually adjust our filtration rate. If we're in sympathetic dominance or fight-flight, then of course nervous control will actually, because that's what the plexus is all about, will constrict the afferent arteriole, and this also will divert blood flow away from the kidneys. Less blood to the kidneys, less urine formation ultimately. Also, we can stimulate the juxtaglomerular cells in our afferent arteriole to release renin, which will increase systemic blood pressure because that is a very potent vasoconstrictor. Now we're into the topic of tubular reabsorption. So we have this large amount of filtrate, and we only want to put out basically 1 liter to 1.5 liters of urine a day. And so we need to reabsorb all of this volume that we've actually put into this tubular system, as well as the solutes that we want to actually keep inside our body. And we will reabsorb glucose, amino acids, vitamins, and most of our ions through an active reabsorption process that couples sodium transport with the movement of these various particles. Now, in order to move these particles into the cells of the tubule, because you want to go into the cells on the luminal side and then from their basilar side into the interstitial fluid, into capillaries that are peritubular or vasa recta. And so those are the capillaries that are normal capillaries that we talked about that are going to put our fluid back into the system, or basically responsible for putting back all that fluid and the solutes with it back into the system in those areas that got taken out. So with the co-transportation of sodium, we are using the sodium gradient to help provide some energy to the movement of various solutes. In order to move these solutes into the cell of the tubular system, we actually have to have on the luminal side as well as even on the basal side to get them in, to ultimately get them into the bloodstream, carrier proteins. And remember, carrier proteins are going to be transmembrane proteins for us. And this is needed to get solute into tubular cells. What's interesting, we actually have only so many carrier proteins, and that's why we have this topic of transport maximum. So the carriers are proteins, transmembrane, obviously with a channel or pore in them to allow the passage of things. And I'm going to draw a goofy glomerulus right here because it looks like a bunch of squiggles to me when I look at it under the microscope. I'm going to draw this big tube going in and this skinny tube going out. That's our afferent arteriole. This is our efferent arteriole. And now I'm going to draw my capsule around this. And I'm going to draw a straightened out proximal convoluted tubule. And then I'm going to draw these little carrier proteins along the side. You know, this is for this purpose, we are actually going to be showing how glucose leaves the filtrate and gets back into our system. So glucose is going to be colored like red dots. And it's going to be part of our filtrate. There will still be some glucose left in the efferent arteriole, but we are going to definitely be pulling it out of the filtrate. And as it now gets into the proximal convoluted tubule, this glucose concentration will go down because glucose is going to go into these carrier protein doors, so to speak. And so we end up with no glucose in the tubular system when we have normal filtrate, normal blood glucose levels, and normal filtration rate. They always are, I think cell phones are designed to actually embarrass you at the most inconvenient opportunities these days. But this is normal blood glucose levels. Well, one of the things that I think almost all of us know about diabetes, even if we don't have diabetes ourselves or in our family per se, we know that one of the tests for diabetes is checking the urine for the presence of sugar. And so what that means is that the amount of glucose in the bloodstream was way higher than what it should be. So therefore, the amount of glucose in the filtrate is also way higher than what it should be. And then as we go down into our proximal convoluted tubule with the various doors that are there, we are overwhelming the doors, and then we end up with glucose ultimately in the urine. And so that's how we overwhelm the system. You have to realize these carrier proteins have a specific size for each and every single one of them. And we have a limit to the carrier proteins that we have. And so if this room was really full, and with like a bunch of everybody was glucose, for example, and we had only 2 regular sized doors, the ability to leave this room is slowed down. But you have to realize the filtrate formation continues, and so it has to continue to move on down this tubular system. It doesn't stay there stagnant. Now we have 2 double doors, which are much larger, and so more people can actually leave this room in a shorter time period than if we actually had only one. And that's to let you know that the size of the doors matter as well as the number of doors matter. And that's what these carrier proteins are all about. We have a finite, so to speak, a limited number of carrier proteins, limited size, and limited time that the filtrate has the time to actually pull things through these doors. And so if we are having a slow filtrate, obviously we can take more out, but that's not typically what happens. Filtration rate, remember, is the same throughout the day. And so things are moving along, and if you have more sugar, you're going to end up with more sugar in the filtrate when it finally comes out in the formation of urine. So that's the story of glucose. The same is true, isn't it, if we actually take vitamin C. Is vitamin C water soluble or fat soluble? It's water soluble. So that's going to be in our filtrate. And so when you take a vitamin C supplement, one of the things that most people typically notice is they can definitely tell when their supplement has more vitamin C than what they need. Because what will happen is you'll notice definitely the change in your urine. And so that means you overwhelmed your transport maximum of your carrier proteins, and you're just peeing out all that vitamin C that your body didn't need because it cannot reabsorb it at that time. And so if you want to absorb more vitamin C, you need smaller doses and more frequent dosing, correct? That would be a better way if you wanted to actually boost your vitamin C level instead of taking a honkin' pill, that's got way too many milligrams of vitamin C for effective absorption of vitamin C throughout the day. Passive reabsorption. Well, that's something that we all know about with simple diffusion and osmosis. So that's basically saying that we do have some protein pores that are going to allow various substances through, and the protein pores that we have for water are called aquaporins. There are channels for water movement. And so sometimes you'll see them listed in older texts or tests as water gates. So water gates are actually called aquaporins, so water channels. And the amount of water channels that you have in a cell will definitely affect the amount of water flowing or in or out of the cell. And it's just basically like if you take a pin and you poke a bunch of holes in something, it makes it more leaky. And aquaporins are really interesting. We can make more or we can make less. So when we make less aquaporins, we have less holes, so to speak, in our cells, which make our cells less leaky for less water movement. Or if we put in more aquaporins, we can actually have more effective water movement. And that's going to be very important as we actually talk about how we make dilute or concentrated urine. Water is not something that we actively transport. That's all a passive transport process. And we all know, let's put it in the notes, H2O follows solutes. Areas in the tubular system that are responsible for our reabsorption of solutes and water. Proximal convoluted tubule actually is responsible for the bulk of the reabsorption, and that makes sense. It's got the microvilli, and so that's an absorptive surfaces. The nephron loop, mostly water. And I'm going to take the word controlled water out, but some of our diuretics are very specific in that they actually work on the nephron loop. But water is a big player in the nephron loop or loop of Henle. The distal convoluted tubule will be we have pulled quite a bit of the filtrate back into the system or reabsorbed it. But whenever we add aldosterone to our system, what will happen is we will pull more sodium out of the filtrate into the cell. And whenever we do that, we know with sodium, we will have water also following that. The last portion of the process of forming the filtrate and ultimately urine is tubular secretion. This is the opposite of tubular reabsorption. Remember, with tubular reabsorption, we're trying to get the filtrate back into us. With tubular secretion, we have some bad stuff that we want to get rid of. And some people say secretion equals excretion. So this is stuff that we want to get rid of. And what's really nice about this process with our kidneys, we can get rid of protons with this method. We can get rid of too much potassium in the bloodstream. We can get rid of ammonia via this method. And so that's what this is telling you. When we are secreting into this, it's still in our bloodstream, and we are literally putting it into the filtrate, which is already formed. So ammonium, urea, creatinine, and others, but those are the ones that I actually want you to know. This cartoon here is just showing you the lovely microvilli for increased surface area. It is showing you again that we actually have protein pores on the luminal and basal side of these cells, of these simple cuboidal cells. And so on the luminal side, that's getting stuff from the filtrate into the cell, and then from the cell into the interstitium for the bloodstream. When we get stuff into the interstitium for the bloodstream, one of the things that you have to remember is we have squeezed a lot of fluid out of the bloodstream, and in doing so, that means the hydrostatic pressure on this side is low, because low volume, and also high osmotic pressure because it's also, again, low volume, and we still have the large proteins as well as the cellular elements actually taking up space for that. And so it makes it easy for our solutes as well as our water, very importantly, our water, to get back into our peritubular capillaries or vasa recta. Here are some important points about how we concentrate our urine. First off, one of the things that you need to know in the formation of the actual formation of urine, you have to realize the osmolarity of the blood, of the glomerulus, and of the filtrate in the upper part of the tubule, the capsule and proximal convoluted tubule, is actually all around 300 milliosmoles. When we take a look at the saltiness of the kidney, and I hope you understand saltiness means higher osmolarity. Remember osmolarity and tonicity? Higher tonicity, hypertonic means more particles, and let's use salt as a particle. So I like to use saltiness as my explanation. The more osmotically concentrated you are, or the more hypertonic you are, the saltier you are. And so we know what wants to follow salt if it's around, and that's water. And that's what helps to regulate water movement. In the deepest part of the medullary area, our osmolarity is 1200 milliosmoles. Folks, that's super duper salty. I mean, you are craving a drink of water when you have that type of osmolarity. And when it says the deepest part of the medulla, it's talking about the apex or the papillas of the pyramids. And indeed, when we take a look at this picture, here we are, 1200 milliosmoles at the apex or the papilla of our medullary pyramid. And if you'll notice, there is a gradient of osmolarity as we go towards the base of the pyramid, and also where our glomeruli are located, we have an osmolarity of the surrounding tissue of 300 milliosmoles, which happens to be the same as the osmolarity of our blood, as well as the first portion of our filtrate. Some other things that we need to understand and then apply as we look at how we get our filtrate back into our system, which is the reabsorption process, is that our descending limb of our nephron loop is impermeable to salts, but freely permeable to water. And our nephron loop, or our loop of Henle, remember, that's in the medullary pyramids. So that's really important. If you're impermeable to salts on the way down, but you're freely permeable to water on the way down into the salty, salty desert of this pyramid, that water is going to move out of that descending limb because that's what's going to pull it, this high solute load. What's interesting then on the ascending limb, it's actually impermeable to water and is going to actively pump sodium chloride or salt out. This is important in what's going to actually happen to the concentration of our urine itself. Then the next thing is, in the collecting tubules, this area happens to be permeable to urea. And I'm going to scratch out tubules and I'm going to put ducts because that is the one that actually goes definitely all the way down the pyramid. It is permeable to urea, so some leaks out and helps with maintenance, the various concentration gradients that we actually see for our osmolarity. The vasa recta are the normal capillary beds that accompany the loops of Henle or the nephron loops. They are permeable to salt and water so that when we are pulling water off and then pumping salt out, we can put these guys, salt and water, back into the vasa recta. So that gets back into our systemic circulation. And now we come to the cartoon diagram of this countercurrent mechanism. So let's take a look at this. Bring it on up. So this is our afferent arterial, our efferent arterial. We know that this is the glomerulus. And then we know our osmolarity, as stated earlier in our notes, of the blood is 300 milliosmoles. We also know that the osmolarity of our first filtrate formed is 300 milliosmoles. So large amount of water, large amount of solutes. And the bulk of the absorption of our solutes and water occur in the PCT. So remember, we're going to get 75% of the filtrate that was formed actually back into peritubular capillaries and therefore back into our bloodstream. It's going to be reabsorbed. What's interesting, though, is noting that the numbers remain the same. So we start off with an osmolarity of our filtrate at 300 milliosmoles, and then when we get to the end of our proximal convoluted tubule, we're still at 300 milliosmoles. What this should mean to you is that for every solute that we pull off a comparable amount of water, so that what's left behind is still the same osmolarity. And all of this stuff is still in the cortical region because that's where our glomeruli live. Our glomeruli live in the cortex. So we can make a little line here if we would like and make sure that we remind ourselves that we're in the cortex above this line and we're in the medullary pyramids below that line. So now we're into the nephron loop. And we are freely permeable to water in the descending limb. And the surrounding tissue, first area that we hit, the osmolarity of that area is 400 milliosmoles. And so what that means is water is going to be pulled out, which is what these arrows are all supposed to depict for you. And as we pull water out and no solutes, that means we concentrate. And so as these numbers are getting larger, they're going to be similar to their environment. And this is important because if we change the concentration of the environment, we'll change the concentration of our filtrate in this descending limb also. So when we get down to close to the tip, we are at 900 milliosmoles. And if we get to the tip, we're at 1200 milliosmoles. Remember, the tip or the apex or the papilla is where the osmolarity is the greatest. Kangaroo rats have double the osmolarity. So what do you know about the filtrate when it gets down here to the tip of this pyramid? It's going to be double. So this happens to be our osmolarity diagram, but other animals have a higher osmolarity diagram. And what's also important is that, kangaroo rats, I don't know if you realize, they hardly make any urine. And that's because they live in a very dry climate. And so their kidneys are designed to maximally concentrate their urine so that they can live in a very desiccated or dry environment. Now, what's really kind of strange, though, is as we go up on our ascending limb, remember, we are impermeable to water on the ascending limb, but we are pumping out actively salt, sodium chloride. So here we go. And when we pump out a solute, that causes our osmolarity to go down. So the numbers go from a high number to a lower number. And we end up at 700. We're still pumping out more solutes. We get down to 400. And even before we get to the cortex, we are down to 200 milliosmoles in the lumen of the ascending limb. So that means we've pumped out a lot of solute. But you guys can realize when we got down to this area right here, we lost a lot of what residual volume we had, correct? So we lost a lot of volume here and concentrated the solute load. And now we're decreasing the solute load as we go up and not having much of an impact on our volume, correct? Now, what's interesting is once we get into the distal convoluted tubule, under ordinary circumstances, without any sort of hormonal application, our osmolarity, we pumped out enough sodium chloride that our osmolarity is now at 100 milliosmoles, which is much less than what our osmolarity is of the initial filtrate as well as our blood. And this stays the same. And so we are not losing any water in this area. It's important for you to realize that. Then we get into our collecting duct. And remember, many nephrons terminate in a collecting duct. So this is just showing you one example, but our filtrate is now at 100. And if we don't apply any hormones, the ultimate filtrate, which will then be urine coming out of the tip of the pyramid, will be at 100 milliosmoles. And this collecting duct and our distal convoluted tubule are going to play actually a fairly significant role in helping us to concentrate our urine. When we become dehydrated, do you guys remember what hormone is produced by the posterior pituitary? Antidiuretic hormone. An antidiuretic hormone acts predominantly on the collecting duct and causes the cells of the collecting duct to create more aquaporins. Because what this diagram here is showing you is that this collecting duct is without aquaporins, correct? It has no water channels for any of the fluid to actually leave because this area here is still around. It's in the medulla, correct? So this collecting duct is in the medulla. And if we don't insert aquaporins into this, we will have the final filtrate leave as urine at 100 milliosmoles. But if we apply ADH and say we're really, really dry, we had a cold, and we slept all night, excessively mouth breathing. And, I don't know how you feel, but when I wake up in the morning after I've not been able to breathe through my nose and I've been breathing through my mouth, I'm feeling pretty darn dry. And so the first thing I want to do is actually grab water. But what's happened is overnight, because of the situation going on where you're getting more and more concentrated because you're drying out, you get the ADH release. The ADH causes more aquaporins. And now let's start inserting aquaporins along this thing. What will that do to the concentration of your filtrate and then the urine? Yeah, water will start to leave, correct? And when water starts to leave, based upon where we are, That's where we'll get our ultimately the potential to concentrate our urine to 1,200 milliosmoles. But that's a heck of a lot of antidiuretic hormone that's actually being released, because that's just shoving a bunch of aquaporins into the luminal side of the cells. So that's what ADH does. It's a hormone that makes the cells make more protein channels or aquaporins for the cells. And that's why when we come to our notes here, changing the concentration of our urine is the biggest thing is antidiuretic hormone. It causes the distal convoluted tubule, but more predominantly the collecting duct. That's the bigger player because it's the bigger player. Can you guys understand? Because of its location? Because it's going down into the land of salt, so to speak. And so if you put more aquaporins into that guy, you will get a bigger bang for your buck, more water preservation. So it makes it more permeable to water because it increases aquaporins on the luminal side of these cells. And so for us, any of our water loss causes increase in ADH release. And when ADH is released, we retain more water because we're taking it out of the filtrate and we're putting it into the interstitial space. And from the interstitial space, the vasorector will actually take it up and put it back into your bloodstream. That's reabsorption of that. So in order to form a dilute urine, we have to decrease ADH secretion or release. And therefore, this will decrease the aquaporins in our collecting duct and DCT. But I'm putting collecting duct first because that is indeed the one where more aquaporins will definitely, or less aquaporins will make a big difference for your urine. Diuresis. When you diurese, that means you make a lot of pee. Antidiuretic means you don't. You hold on to that. So diuresis is the actual formation of dilute urine when we diurese. And there are two ordinary substances that you can encounter in your environment, and one is alcohol and the other is caffeine. Where they work will impact what happens. Alcohol inhibits ADH release. So as you drink alcohol, which is a drying agent, which is really interesting, it causes you to actually not release ADH as well as you should, and therefore you actually create more urine. Caffeine inhibits sodium reabsorption. And you have to understand sodium reabsorption is throughout that tubular system. And remember, it's a solute. So if the solute stays, because inhibits reabsorption, if you inhibit the reabsorption, which means the removal of the solute from the filtrate, then that means you have also more water in the filtrate. And so that's how caffeine works. It inhibits sodium reabsorption, and therefore you will actually have more urine or water present in your filtrate and then urine. Moving along at a great clip here. Chemical composition of urine. Well, most people know the bulk of it is actually water, and then about 5% or less even is solutes. And what's interesting, most of it is from urea, which is a product of the breakdown of proteins. Now going to the remainder of the urinary system, ureters, urinary bladder, and urethra, all designed to contain urine. And our ureters indeed have a normal mucosa for this system. And what would be a normal mucosa for this system? How about transitional epithelium? Yeah, So transitional epithelium is actually here in our with our ureters, and then we have a muscularis layer, and that's smooth muscle, and that's there to help actually create peristalsis. So we literally will squeeze our urine all the way down to the urinary bladder. And the outer aspect is adventitia. And one of the things that you should realize whenever you see the word adventitia, that is indicating that it's not in a cavity that has the typical serosal lining. And so again, this is consistent with everything being retroperitoneal. Our urinary bladder is described as a muscular sac, again, smooth muscle, located on the pelvic floor. And so that's what this is meant to show you right here. That area is the pelvic floor. I'll erase my marks there. It has a very special area at its base. It's called the trigone. The trigone, three things are present, and that is the openings of two ureters and the opening of the single urethra. And that's at the base of the bladder. So our ureters don't hook into the top of the bladder, they hook into the base of the bladder. And this is important to actually prevent reflux. This mechanism is designed to prevent urinary reflux, backwards flow of urine, because urine's supposed to be flowing all the way down to the bladder, whether you're standing on your head or whether you're standing upright or whether you're laying down. What happens is as the bladder fills, it becomes heavy, and it actually starts to add weight on the little ureters that are coming into the base and compresses them and forms kind of like a pseudo valve in that area. So when people have reflux in this area, part of the problem could be that the ureter is not coming in at the proper area or angle to this. And so that's an important aspect to keep us from actually having reflux of urine. So that trigone area is very important. So here are for the ureters, and then here is for the urethra on the female bladder, same thing on the male bladder. And so if you haven't already done so, you should open up your cat's bladder and you should take a look down at the base. It's going to be very small, but you should be able to follow, if you can't see it at first, you should be able to follow the ureters to the base of the bladder and see on the inside where they actually open up. Very, very small openings or apertures for that. The bladder wall indeed is transitional epithelium folded into rugae. We have a muscularis layer, and the bladder muscle has a special name. It's called the detrusor muscle. So the detrusor muscle, whenever you hear the word detrusor, automatically should think bladder. That's the smooth muscle of the bladder. And then, of course, we have adventitia because the bladder is also retroperitoneal, the outermost layer of that. Let's talk about the urethra before we go into the literature on that. And obviously, you can figure out which is by just looking at the urethra, which is the male system and which is the female system. The female system is only a few centimeters in length. The male system is 3 to 4 times that length. And we have sphincters associated with our urethra. And take a look and see if you can on your notes, if you can't see it too well on the slide up here, see if you can find how many sphincters there are. Two. And which one is closest to the base of the bladder? The internal sphincter is closest to the base of the bladder in both sexes, correct? Mm-hmm. Now take a look at the external sphincter. And where is it? Is it located in essentially the same area or the same distance, shall we say? Is it the same distance from the base of the bladder for the external sphincter? Yes. kinda, but not really, because there's something between what's called the pelvic floor and the external sphincter for the male, and that's the prostate gland. And so we have a length of prostatic urethra that's there, and on the other side of the prostate gland is where the external sphincter is located. But I want you to understand they're both in what's called the urogenital diaphragm. They're both in the muscular floor, correct? And so our external sphincter for male and female are both in the muscular floor. It's just that for the male, it is actually on the other side of the prostate. It is not as close to the base of the bladder as actually the female's is. So that's an important difference for that. So the prostate actually is kind of a spacer in between the base of the bladder for men, and we don't have that type of tissue spacer for women. And then, of course, the urethra then goes through the bulk or the body of the penis, and that in itself actually increases the length greatly. And that's what's bringing us down to our final topic, the urethra, a thin-walled tube that drains urine from the bladder. Wall, that is fibromuscular. So we still have smooth muscle in the wall for peristalsis. Mucosa, mostly pseudostratified columnar, and I have to tell you that that is more for male, which is really interesting because it is transitional near the bladder and stratified squamous near the opening. And I'm referring to the external opening. Indeed, we have sphincters. The internal sphincter, which you located at the base of the bladder, is smooth muscle. So that means it's not under voluntary control. But the external sphincter is skeletal muscle, and that indeed means that it is under voluntary control. And that brings us to what's called micturition, which is another term for voiding or urination. Because we actually do have a micturition reflex. Can I finish it? It's close to, okay. So when 200 cc's accumulate, this reflex is initiated. And so this reflex will have relaxation of internal sphincter plus contraction of the detrusor muscle. And remember, the detrusor muscle is the muscle of the bladder wall. So our bladder's gotten swollen up like a little balloon, and now the detrusor muscle will contract and the internal sphincter will relax. In order to void, you must voluntarily relax the external sphincter. When you realize that you can control that external sphincter, you're effectively potty trained when you're a little kid, and everybody's happy in the family because they don't have to buy so many Pampers and stuff like that for you anymore. A nice cost savings to parents. So, external sphincter control, important in voiding once you are able to actually control this. Now, your bladder can actually double in size, so we can put in another 200 cc's of urine before this reflex will start to kind of pound on your door of consciousness that you actually need to do something about it. And so we can train our bladders to actually even hold more than that, but that's typically where we actually end up, is around 400 cc's. Most people will say it's time to go, got to go to the door. So we're done there, and thank you for letting me finish.